Io aspetta. Sì, molto bene. And on. Okay, so we proceed with our study of the characteristic polynomial of this random entire function. This is the main object of our study. And so you can see that it is a product. It is a product of. It is a product of some quantity over the particles of our process. And so we can start with studies. We will be interested, in fact, in objects of three kinds, quantities of three kinds. So first of all, well, obviously this one is, for example, it's a product of some quantity over the particles. So this will be one of the main objects of the whole discussion. So what I call multiplicative function. But this will not be enough for us. So, of course, together with this multiplicative function will be its cousin, additive. Additive function. Additive function. But this in itself would not be enough for us. This in itself would not be enough for us. We will also need multiplicative functional over pair. So one object that we will need, I will develop psi g 2 of x. Let me denote it maybe q. And let me write like this inside of the product 1 plus q of xy, where xy are in x and are distinct. Or you can think that if they coincide, q is equal to 0. Also, of course, we need this sq2, which is the sum of q x, y, x, y, and x, distinct. So, and we will have different.
Just a question. The big X was the space of eigenvalues, isn't it?
As it does. So X is just, at this point, one can think about X as just a collection of particles, just subset of, let's say, the line for clarity, but it can also be some other thing without accumulation. Subset of, let's say, R. It can be something else. It can be C or the D, C, D, very different possibilities are interesting without accumulation. Without accumulation. That's exactly right. That's exactly right. For example, in case of disk, it can accumulate on the boundary, but yes, it's a discrete set.
Oh, thank you.
Okay. So let me explain why. Let me first, before passing to precise things, let me explain the motivation. Let us look again at the formula with which we started last time. Product e to the I theta k minus e to the I theta l squared. let us now imagine that we act on the circle by some diffeomorphism. So imagine that we act on the circle by some diffeomorphism. What will happen? The measure will become this would be the Kroger measure. Right. So, if we want to compute the radon negative derivative, then radon negative derivative is the product of CF So this is product over pairs of products. This is product over pairs of products. This is product over pairs of products. Yeah. And then there is product over individual particles, the chain. So in order to study the action of the group of diffeomorphisms on our process, we need to study the action of we need to study the behavior of multiplicative functionals in two variables at a time. Of course, these formulas can perfectly well be written also in the case of infinitely many particles. But the question arises whether those infinite products diverge. And this is exactly the question that I would like to address today. Okay, and it turns out that in fact, everything can be taken out of a very simple probabilistic property, which is more general, which the determinantal point processes have, but also other point processes have, not only determinantal, which is the property of negative correlations. Negative correlations. What does it mean, the property of negative correlations? It's a very simple, very, very simple property of negative correlations. Just the property is the following. It's for very general points, just for some probability distribution on space of subsets. One can consider it in many very general situations. So this is the point. Imagine I have my space. Here it is R, and I cut it into two parts. So I and J, or in fact I write for 2, but in fact it's also 2 for more. And I have two functions, f and g, and these functions are increasing. What does it mean increasing? These are functions depending, so increasing functions. So f of x in respect to I and G of X in the solution of G. That is to say, it's a function of a subset. And if I add one more part of the subset, then the function increases. So it is increasing with respect to the partial order on subsets. There is partial order on subsets given by inclusion. So the function is increasing because of that, in this sense. Okay, so increasing positive, positive. Function is positive. Okay, the condition of negative relations is the following: the expectation of G is less than equal to. This is the expression of the property that eigenvalues repel. Repel each other. This is what we discussed informally last time. Eigenvalues don't like to be near each other. When there is an eigenvalue, it repels. So this is an expression of this property. So conditional probability, subject to the condition that there is something in a different spot. So this something exercises a negative influence. Right? Does it make sense? Does it make sense? Yes? It exercises a negative influence. Of course, one can also write a similar property for M.
Let me just clarify, Sasha. So
Yes,
this condition is a consequence of the monotonicity conditions of F and G.
That's exactly right. That's exactly right. That's exactly right. That's exactly right. This is very important. Yes, of course. Yes, otherwise it's not possible for such condition to hold. Yes.
I'm sorry, Pedro, can you repeat that?
So let me give an example. So if we have a part, just one particle here and one particle here, as we know, the infinitesimal probability is the determinant. So it is the determinant kxx, kyy, kxy, and kyx, which is equal to kxy. So this is equal to kxx, kyy, minus kxy, so it is less than the product of the probabilities, right? So the fact that there is a particle at a given site is less probable once there is a particle at the opposite. It's less probable. Have I answered your question? Those questions, yes?
No, it was only to repeat because it was not very.
What I asked is if the inequality will be low, what's the consequence of the increasing assumption?
Which it is. Which it is. Which is very much is. Yes.
Okay.
Which is very much is. Yes. Okay. So now I want to explain a very simple fact. I want to explain a very simple but very useful fact. That this property of negative correlations in fact allows one the property of negative correlations allows one to estimate the distribution of additive functionals. So first, most immediately important for us are multiplicative functionals, but multiplicative functional is exponential with an additive. So in order to study multiplicative functionals, we first need to study additive. Okay, so okay, so let us assume, so we study additive functionals starting from occupation numbers. So first we need to estimate properties of occupation. So occupation number, let us recall, is the number of particles in an image. Number of particles in And in fact, this number decays, the tails of this quantity decay very fast. It is subnormal, and in fact, it decays even faster than that. It decays even faster than that. It decays even faster than that. What I want to say now, so let us just write the following. Let's just write the following statement. Let's say that this is less than some, well, there is linear term. And then there is some function, phi. Key example, key. Example is just subnormality. So please observe that this is very different from Poisson process. So some quantity, some constant, delta lambdas. Delta depends possibly on something. So I want to say that in this case, so let us start with theta. It's a proposition. In this case, I need an estimate. I need a so let f be a function such that. And let us here, let I be an interval with of the form k plus 1. Again, this is just for completeness of this question. So just interval between two consecutive integers. Let f be a function such. Of, well, I write maximum like supremum, so maximum f square x is less than infinity. So then the range is such more to infinity. Right? And this is less than. Then I claim that the random variable SF minus expectation minus the expectation itself is itself subnormal. Expectation of exponential lambda is less than exponential d lambda square 2, where d depends on this delta. Let me now assume that delta, where d only B only depends on. Excuse me, I didn't write this very well. I also have this, excuse me, I also have this excitation term which I wrote here. Where T depends on C. So this is our this again. Let us look at the proof of that. So what is the proof, as you will see, is this. What is the point of the claim? The point of the claim is that one can work with additive functionals starting just with occupation. Starting just with. Okay. So first of all, it's enough to consider F positive. Because we can write this for, we can prove this for F positive and negative, and use should be positive for us. Enough to consider F positive. Second, so then there is a little bit, so let us consider F supported in such I. Let us start with F given this. And support F in, let's say, 0. So let us also assume that F is less than 1. Then, of course, we know from here that expectation of lambda itself is less than e to the c lambda plus delta lambda squared. This fact we know. Observe, however, that we also know just from this very fact, we also know it follows that e to the lambda SF minus expectation is less than some e to the delta. So, in order to avoid writing many tildes of primes and so on, let us agree for the purpose of this talk that delta is not the same from one problem to the next, like double or something simple. So, okay, so why? Why? There is a little, there is a little subtlety here. In fact, we can write this expectation. It is 1 plus, we can write it in Fourier space, lambda square times this very expectation for some intermediate nu. That's it. right? So this is just Lagrange formula for a Taylor formula in the form of Lagrange. But then, of course, for small deltas, this won't be. For let's say lambda less than 1, this one is bounded by system, and so we have such estimate. And of course, for lambda bigger than 1, such estimate also. Please observe that we want a very important thing. We want a very important thing because we want lambda square. Because here, so this is this square. It's very important. You will see why it's very important. I will say this. We will see. I will say in a minute why this square is really effective flows from the formula that I just raised. I will say this. So I will say this very clear, very explicitly. So, okay. Now, of course, here we see the supreme of f less than 1. It follows also that delta supreme f square because lambda is a square. Well, and now the formula is clear because this is exactly the same formula. Now we just use negative corrections. So one can see the power of the fact of the existence of negative corrections in that. It immediately gives us possibility of transition from occupation number to additive function. So for additive functional of two particles, it will not be so obvious. Okay, so now I consider additive functional of two particles. Before I do it, let me just point out, let me just point out that the very same truth works for general also functional. For general basis of the neural lambda, same truth, the same truth, works. The only thing one would need is that 5 lambda, so under the following assumptions, 5 lambda has to be near 0, it has to be less than a constant 5 lambda provided. Five lambda is greater than C lambda squared on 0, 1, and 5 lambda is greater than lambda always. In order to make the estimated infinite. So if one substitutes instead of lambda squared 5 lambda, the very same argument follows. Unfortunately, this is all fantastic, but not quite sufficient for us. So for additive functionals of one variable, we control them in great way. But this is not enough for us. So we need, as follows from the formula. Okay, is this clear? Can I erase all this? Is this okay? Erase all this and start fresh. So as follows from the formula that I just wrote here, so let me write it again. We need multiplicative functionals of two variables of the following form. We need to study multiplicative functionals in two variables, functionals in two variables of the following form. As it follows from what I wrote before. Problem 1 plus, let me write it as omega x minus omega x minus 1. So this is very interesting for, well, squared, but it doesn't. This is very interesting for here. Let's recall that I write as f of x in the form x. Please observe that even convergence of such multiplicative functional is not obvious. It's not obvious that such quantity converge, even if omega is a constant. It's not obvious. It's not obvious that such quantity converge. And this is exactly, so to speak, the tricky part. So, okay. So, how do I study such multiplicative function? How do I study such multiplicative function? So, the point, let me say this. So, as you just saw, in fact, that for the additive function, let us start with the function of E1. Let us start with the function of 1. So, as you saw, the subnormality of the additive functional was given in terms of some, so to speak, L2 type norm. So in terms of this one. In fact, for sign process, it is possible to give a much more precise description, but let me stick to general setup. So, in particular, let me say, for example, expectation of additive functional is equal to integral of f. So it might seem that the natural condition for integrability of additive functional is integrability of f. Well, except in fact, no. So this is the whole point. So this would not be enough for us. This would not be enough for us. For us, we need additive functionals, not absolutely convergent, but oscillating. And this we need precisely in here for the action of the group of diffeomorphisms. So also, in fact, this is what we need in the very main object of our study, the characteristic polynomial. It's an oscillating function. So we need to control these oscillations. So, and in fact, for example, the variance of this additive function, can be written in very beautiful form. It's a little exercise with the determinantal. Again, it's just exercise question. And it is computed like this. So in fact, it almost might seem like a paradoxical situation. The variance is well defined, whereas the expectation is not. So in fact, the quantity normalized additive function. Such situation arises a lot. I don't think this is the only. Normalized additive function can be defined in much broader range of situations when this quantity is not defined. So, for example, taking f equal to 1 over x. It is convenient 1 over x is not great for me because we can singularity is 0. Let's say 1 over x plus I. Taking a function like this, the integral diverges. But this is exactly the function that we need. This is exactly the function that we need, but this integral converges very much. This integral converges very much. It is essentially Sobolev 1/2 norm. So it converges, but even without a Sobolev 1/2 norms, it is immediately to the integral. Sine squared pi x minus pi x minus square yes y. It is immediate to see that one gets the x plus 1 dy y squared plus 1. It converges. It converges. It converges. So this how to say, this additive, normalized additive functional is defined under much broader assumptions than the additive function itself. And the same works here. This additive functional in two variables, it can only be defined in principal value. So in fact, it is convenient. One can prove similar formula. It's not as simple. I will write it down. So it's not as simple. It's not as direct. It's also not inequality. It's an inequality, but one can prove the formula. So the variance of similar u xy of the variables, the variance of SQ is less or equal than the norm of u L2. But this is not enough. In fact, there is one more term, and norm of what I call IQ, I'm going to spend in L2 of I squared, where IQ is the following quantity. So the integral being understood in this way. This closely makes perfect sense, for example, for the station. So normalized additive functional can be defined even when usual additive functional is not defined. Usual additive functional is not defined. This is absolutely key point of all this study, that normalized additive functionals, how do I say, this is the whole point of this type of point processes, that their divergence from equilibrium is very slow. Their oscillation from equilibrium is very small. And so the additive functional is well defined. Normalized additive functional is well defined, even if the additive functional itself is not. So this means precisely that one can make sense of summation in intrinsic value. It's precisely this. Okay, let me also very briefly make a very brief observation, and then we will go to a more detailed study of additive functionals for this specific problem. Let me just, in terms of generalities, make the following observation: that these quantities have a certain degree of continuity. This is very important. Let me explain this more clearly. Okay, can I erase this part for generalized functional? Does that make sense? Yes. So continuity of additive functions. So you see. So let me put it this way: topology on the space of configuration. Topology on the space of configurations and continuity of additive. Let me stick with R and continuity of additive functions. Okay, so there is standard topology on space configuration, which is just topology of projective limit. Or put it in a different way, what does it mean? Configuration? Configuration is a measure. It's an atomic measure. So just put unit mass in each point of the configuration. And then topology is given as dual topology on space. It's a continuous function, so forth. Configuration is viewed as a functional or on a space of continuous functions of complex support, and so there is corresponding topology. So neighborhood of a configuration, there's many continuous functions. So a sequence of configurations converges to a limiting configuration if for any continuous function of complex support there is convergence values, or even in a simpler way, what does it mean that configuration converges? Well, there is just one little tricky part, but essentially configuration converges means that in compact part, all particles converge. So it converges on compact sets. So the delicacy is that there are boundary effects. That's why it's convenient to speak about continuous functions. The delicacy is there are boundary effects. Maybe there is some point. So, but just that's why it's more convenient to speak about continuous functions. This is not enough for us. This is not enough for us. This topology is very nice, but it's not enough for us. So the additive functional, my favorite additive functional, is not continuous. So this one, my favorite additive functional, is not continuous with respect to this. It's not continuous, but that's what we mean. So we do need to speak by force of will to make this continuous. We do need to add. So we say that our configurations, our space configurations is configuration for which this converges. So these are balanced configurations. And this definition is supposed to be a continuous function. So the topology is enforced. So this is required. This is part of the definition of history. So then also for functions of two variables, if I have a function of two variables, this one. Then it also becomes continuous because how do I explain myself? So how do I explain myself? I want to say I make this as the following. So I have sums of the form. I make sums of the form. I just let me say this. It's very clear, but just let me say this very precise. So here I have summation over the square of the square of the line. So clearly, so I have the same configuration. So x and y are particles of the same configuration. So it is convenient for me to represent like this on the square. But in fact, I'm representing a product set. I'm representing not just some subset of the plane, I'm representing products. Now, the point is that cancellations are very subtle. It is not enough. So first approximation for this quantity is the following. That's just naive approximation. This would be just some omega k minus omega k cell and number of particles in I, number of particles in I. So this is from I is. So this is very nice, but this is not enough. This is just fantastic, but it's not enough. It's not. What do you mean not enough? Excuse me, let me say this. Of course, it is very. I can stop the game when I have functional which converges absolutely. So once I arrive to a function, so here the whole point is that what's the difference between this and, for example, this? This function just converges absolutely. There's no question about its behavior, right? So just this function, on the other hand, is precisely the subtlety of the problem. So, for example, for Bufetov, this will not converge. This will not converge. There will be too much, sometimes oscillation will be too high. So the Here, on the other hand, if this one if this one I discretize, then the difference will converge. The difference will converge absolutely. In fact, one can see this. So let me just be very clear on this. It's very simple.
So, let me ask you one question. So you first defined this the topology of the space of configuration. Then you said that the first additive solutional is not continuous.
So I need to make the topology stronger.
But you're still going to define it. This is my question.
As I said, I define topology. So again, how I define topology? I define topology by taking a collection of functions with respect to which it is dual topology.
Which it is the
Dual
topology.
So, and I say that my functions are, first of all, compact and in fact integral continuous function transport. So these are included. And secondly, this one. I just added, so to speak, my first one. I added my first one. I say just so sequence of configuration converge to linear configuration if, so to speak, all bounded continuous functions validated, all absolutely convergence continuous functions validated, and also this one. So all, excuse me, when I say all absolute convergent, I mean convergent. I need to, of course, specify speed convergence, otherwise all functions. So this one validates it, and this one validates it. So to the space of, excuse me, to the space of continuous functions of compact support, I add all functions that decay at this speed, and I add this function. This is my topology. Yes, this is my topology. This is my topology. I add these functions. So and then this then the definition of this functional is.
I have another question.
Yeah.
What is so special about this function? So instead of I, you move the I.
No, of course.
So
It can be any function, so it can be any.
The function is the same.
Of course. So it can be, of course. Yes. So any function, yes, they were right. Description, any function lambda x, where limit x number x. Just a second. I want to say that x squared number x minus x no, it's not zero. Let's soup this one. Soup this one. Yeah. Yes, it's clearly. So any, I can use any function. Yes, let me your this example. Let me reverse. So I can use any function. So first of all, the topology. First of all, the function of complex one. This. Second, continuous functions of the form b of t the square root of 1. Rebound. Third, continuous functions of the form lambda t, where supreme of t square lambda t minus t is less than. So in other words, what it means that lambda of t at infinity is 1 over t plus O larger than 1 over 3. At infinity. Now, of course, it can be 1 over t plus I, 1 over, so t over t squared plus 1, anything, you know, t over t squared plus 1, anything, this t 1 over t plus I, anything. So now, my point is that I want to see, so this is what I require. And so please observe that for functions, so let me just proceed with what I was saying. That for 1 over t plus I, for example, I can discretize sum k over k plus. So to speak, instead of values, so instead of my function, I take value at each leftmost integer. And so the difference, it is not very difficult to see that the difference is, so sum of them. In principle, right? Minus. That's some sum over, or some constant sum over plus 1. Does this make sense? Because I subtract at each x, I subtract the value of k, so I get something like this per 1. Because difference between x and k is less than 1, right? Okay. So now I want to play with the same game for 2 variables. Now I want to play the same game for 2 variables. But there is a subtlety. There is a subtlety. It doesn't work like this. It doesn't work like this. So one can see this. So in fact, let's look at this. Sum minus this. It will be too much. The difference will be too much. I can explain this in the following way. If we consider this quantity, and we take the derivative, let's say in x, what we get is omega prime x. But we still get x minus 1. So this does not converge absolutely.
What do you get with x minus y?
Because when you differentiate and fraction, you differentiate numerator and denominator. Then of course you differentiate the denominator as well, and that's perfect. And that quantity converges absolutely.
You are understanding the asymptotic behavior.
Please again?
You are understanding the asymptotic behavior.
That's exactly right. That's exactly right. Yes, that's exactly right. Yes. So, okay. So, in fact, I need to approximate in smarter way. I need to approximate in smarter way. I need to approximate in smarter way. I need So the idea is very simple, in fact. The idea is follows. So if I have my function, well, here it has a special form, it's important for me, but in fact, it's for general. If I have my function, if I have a function of the square, I can approximate it by function which depends on only one variable, function which depends on only the other variable, and then the difference, it will be second derivative. Okay, so I'm saying something very simple. So let us stick with our, so this is my function. So I have my function. So I approximate it. F of x, y. Let's say 5x, 5x. This is my point. This is my point. So I take the value of function kx, ky, ky, excuse me, y xl, this is xl. Here I have k, this is x, yeah. So, and I say that x1 just a second, 5x L. Excuse me, I'm just saying something. $5xL is approximately equal to just just I'm just saying that 5x1 plus 5kf minus 5xl minus 5ky over obviously x minus k 1 minus 7 is approximately to the second derivative of I, that's why the x1 does. Right? Yes. Yes. So precise. So I am approximating. Yes. I am approximating my function with functions only depending on one of the variables. So instead of this, so this is not good enough. This is not good enough. But I approximate, I take, so to speak, next level. I say, I take. So neighborhood approximation doesn't work. So approximate up to the second. Approximate up to the second. Up to the second. So I need to write the sum over omega x minus omega k over x minus k. This will be 1. So one of the variables subtract and the other go. Then I write the same for the other one. And then I add the naive discrete approximation. And like this, I can approximate, and this gives me the desired continuity of any functional interval. This method gives me the desired continuity of any function intervals. Okay, so next, now that we have looked at these additive functional, the next step that I would like to explain maybe is just this: in what sense, in what way. So I would say I would like to explain the specificities of this. Was, as you see, a very general discussion of additive functionals, in fact, we only use negative relations, we need to use any specificity. Right now, I want to become very specific and go to the sign process very specifically and explain the how to say, explain in what sense the different values of my random entire function. So what have we gained so far? The key point that we have gained so far. So this is the entire function that we studied. We have gained so far that the values of this entire function, well, in fact, we need to go a little bit away from the real line, but that's okay. The values of this entire function are subnormal, But this is not good enough. What we really want is that they are also, in some sense, supernormal, to some extent, supernormal, and also that they are also, to some extent, as I say, supernormal, and also that they are, to some degree, in a certain very precise sense, independent. And I think I mentioned this in the very first class, that the independence is hierarchical independence. Independence of, so the picture that one needs to keep in mind, that different values of this process behave in the following way. This is a very beautiful picture, and just this is what one needs. So we imagine a binary tree, and let us imagine, for simplicity, for very simple, to be just very naive, that in each vertex of binary tree, I have just Gaussian random, standard Gaussian random of the limit. Then, of course, the paths in this binary tree will not be independent. Because any two paths, they have a common piece. Yes? So they have a common piece. But after they leave the common piece, they do become independent. And this is.
Can you clarify what you mean by independence of values? You mean
For different t, for different t.
Okay.
For different values of t. This is a random function of t.
T as a random variable
Of x. So the randomness is an x. The function, it's a random entire function.
Okay.
The randomness is an x, the function is a function of t. T is the function. So we will see in what precise sense these random variables are independent. Let's say, are close to being independent. Yes?
Sorry again.
We will see in what precise sense these random variables are close to being independent. Close to being independent. In what precise sense these random variables are close to being independent.
Can you again compare the I guess you were drawing this picture to give us a flavor of the behavior here.
That's exactly right. That's exactly right.
Can you,
That's exactly what I'm going to do. That's exactly what I'm going to do after this one.
yes.
So to be very, very vague right now, we will need to consider to take Fourier transform and to consider different frequencies. So we will need to take Fourier transform in t. We will restrict ourselves to the real line, but not to the real line. We'll the shift of the real line. But that's just we'll consider frequencies, and different frequencies become essentially independent in a very precise sense, as long as t's are sufficiently different. So lower frequencies are independent only for distant variables, sufficiently distant. But high frequencies become, when t's become distant, they become independent. And we will see it for instance. Okay, so let's take a little break, maybe like 10 minutes.
Okay. Ciao.
A possibilidade das bolsas de FCT também. Para falar na
Não lembrei,
eu vou responder uma coisa parecida.
Sim. Como é que estás todo o tempo? José? Diz? Como é que estás todo o tempo?
Tudo bem, daqui a meia hora.
Ok.
Daí, às 5 horas. O Pedro Soares tinha avisado que tinha mesmo que sair às 5.
Ok.
As soltas, as personalidades. Ele tem, eu descobri que o curso mais parecido com este ele tem um curso em 5 partes no ICTP, que está disponível no YouTube.
Ok.
Quando eu estive a discutir com o Pedro Martins, Pedro queria assistir ao vídeo da primeira.
Esse curso é de quando? Porque este curso
Eu ouvi
É porque eu estava. Este processo é entrado no resultado porque eu vou. Bom, está marcado desde 2019. Tem que ser uma coisa recente.
Não, mas ele tem.
Como? Fazer para tirar. Eu sei. Ok.
Para não falar nada.
Mas se já.
Do curso de CTP final da organização. Que tem um professor antes de terminar o processo, mas num outro contexto. Vamos dizer que eu não percebo muito bem. São os cursos de iniciação da organização. Esse curso de CTP era uma escola, um workshop, a teoria de matrizes alimentar. Acho que o CTP é uma coisa.
Então, não nem justo. Isso bom. Eu comeria um cheesecake. Não seria bom?
Sim, é.
Mas eu não costumo contar calorias, mas estou indo a fazer bicicleta na academia
Sim.
e te mostra, né? Te mostra que 1.300 calorias. Aí eu saindo do almoço, comi um sorvete, 1.300 calorias tem um sorvete. Sim, a mí me compensa, né? Eu preciso que me façam comida gostosa com menos calorias.
Tens de fazer doces sem açúcar.
Como?
Tens de cozinhar doces sem açúcar.
Ah, mas
Fazemos
não
isso.
faz sentido, não faz sentido. Você está falando, coisa que não faz sentido. Está falando que coisas você se açúcar.
É como cerveja sem álcool.
Claro, é suficiente que tome café sem cafeína.
Não é nada disso. Eu acho que depois nós temos que fazer uma edição disto, tá? Isto é esse intervalo, faz muito sentido estar aqui.
Se calhar para a gravação.
Ou eles podem apreciar uma combinação de calorias.
É uma falta justificada. É.
Já paraste?
Não. Para ver a logo meio chute a deixar aqui uma mensagem.
Ok, mas tipo, conversando, se calhar vamos parar a sessão agora, para gravar, está bem?
Eu acho que deves ter tirado aí alguma coisa.
Fiz.